So today I'll be programming the Raspberry Pi and BrickPi3 with the EV3 infrared sensor to seek and follow this EV3 beacon like this. I also attached the beacon to an EV3 robot so that one robot can follow another just for fun. And we'll also demonstrate how the sensor can be used to keep a robot within range of the beacon. Here we'll see that the BrickPi3 backs away from the white robot until it reaches a predefined radius and then comes forward again. I'll be assuming that you've already assembled your BrickPi3 and completed the setup on a Windows PC or Mac as described in the Dexter Getting Started page. If not, you'll want to complete those steps before continuing with this tutorial. The Python drivers come installed on the BrickPi SD card that you created in the Getting Started steps. So once you've booted from the SD card, you're ready to begin programming. The Pi requires a lot of power, so it's good while you're programming to have it plugged into a power source other than the battery pack that comes with it. The optional power supply that Dexter sells is a good option. Of course, you won't want the robot connected to power while it's moving away from the computer, so you'll want some rechargeable batteries for the battery pack. When the BrickPi3 is properly powered, the LED next to the power supply blinks once per second. When the batteries are getting low, it blinks more frequently than that. At this time, you could connect a monitor to the Pi desktop and program directly from there, but since we don't want the robot to be connected by wires while we're testing it, we'll access the Pi desktop over Wi-Fi. So we've got the BrickPi on the network and ready to go. So we start up the BrickPi desktop by typing in dex.local. Launch the VNC server. And bring up the Thani development environment. Let's open a new file. And we can start coding. We'll begin with some import statements. BrickPi3 defines the calls we're going to make to the infrared sensor and to the motors later. It's defined in a file called home/pi/dexter/brickpi3/software/python/brickpi3.py. And you can learn a lot about the BrickPi3 system and all the functions available and how the system works by examining this file visually. Next, import sys is required because we'll be calling sys.exit in the program, and import time because we'll be calling time.sleep. So let's do Control S to save, create a new folder called Python in the Documents folder. We'll call it infraredseek.py. Next, we'll create an instance of the BrickPi3 class. We'll be using this class later to call sensor and motor functions. By convention, we'll be putting the infrared sensor on sensor port 4. So we'll initialize it on port 4 in seek mode. We can operate the sensor in one of 3 modes. In proximity mode, it detects a physical object in front of the sensor and tells the program how far away that object is. In remote mode, the sensor detects button presses on the beacon device. In seek mode, or beacon mode, the sensor detects the heading and distance to the infrared beacon. That's the mode we're interested in. Next, we just need to add a few variables that we'll be using later. Beacon distance and beacon heading will be used to keep track of the distance and direction between our sensor and the beacon that we're tracking. As our robot nears the beacon, it stops when it reaches a certain distance, and we keep that distance in this variable, stopping distance. We're programming the robot to stay within a certain vicinity of the beacon, and that's what this variable is used for. And max power is the amount of power we want to give the motors. I played with some numbers and this one worked best for us. Homing mode is true when the sensor is seeking the beacon, and vicinity mode is true when the sensor is trying to get away from the beacon but stay within the vicinity. By convention, our motors are on motor ports B and C. And we have self-explanatory functions that tell the robot to go straight backward or to go straight. We'll see those used later. The next function is the turn function, used to turn the robot toward the beacon when we're heading to the beacon. So the sensor returns a heading value of -25 to 25, where minus 25 means the beacon is to the far left, 0 means it's straight ahead, and 25 means it's to the far right. So we stop the left motor to turn hard left if the beacon is to the far left, essentially by subtracting max speed from itself. And we do the same thing to the right side if the beacon is on the far right. And for heading values in between those extremes, we slow the left or right motor accordingly. So the turn function gives us a nice smooth turn regardless of where the beacon is. These next statements start the program off in homing mode, where the sensor is seeking out the beacon, as opposed to vicinity mode, where it's trying to get away from the beacon. Okay, here's the heart of our program. We start a forever loop, and we interrogate the infrared sensor. We print the return values in the output window just for diagnostic purposes. The sensor returns heading and proximity information for all 4 beacon channels, but we're only interested in the first one, channel 0, so heading in 0, 0 and proximity in 0, 1. If for some reason the beacon is not found, the sensor returns minus 128, so if that happens, we'll break out of the loop and end the program. The rest of the program is pretty simple. If beacon distance is less than stopping distance, that means we were in seek mode and we've gotten too close to the beacon. So it's time to switch to vicinity mode. Otherwise, if beacon distance is greater than max distance, then we were in vicinity mode and we've gotten too far away from the beacon. So we want to switch back to seek mode. Regardless of whether we've decided to change modes or whether we stayed in the same mode. If we're in seek mode, we head toward the beacon by going straight or turning, depending on what heading the sensor returned above. Otherwise, we're in proximity mode, so we go straight backward, backing away from the beacon until we hit the max distance limit, the radius that we wanted to stay within. Next, we sleep for 20 milliseconds to avoid overheating the CPU in that tight loop per the Dexter example programs. We ignore any sensor errors just to keep the program simple. And we can end the demo by turning off the beacon, which causes the sensor to return a minus 128, which breaks out of the loop and falls down here, where we instruct the BrickPi3 object to turn off the motors and exit the program.